we're going to conclude what we can take out of this, what we need to go moving forward, what we need to research into further. So first off, let me talk about an extremely important functional group that our research really focuses on, and this is CF3, the trifluoromethyl group. The trifluoromethyl group has very important pharmaceutical applications. The reason being, its chemical structure is such that it can influence the compound around it. And in many ways, it can make a drug compound that it's put on more efficient. Two ways that I'd like to highlight are, first of all, it can adjust the compound's conformation. So this is important because, as you know in biology and chemistry, structure determines function. So the conformation of a compound can allow it to bind to a toxin, and as we demonstrated earlier, that's extremely important to get those toxins out of the body, or at least find out where they are. So that's one thing that the trifluoromethyl group can do. Another thing that it can do is adjust the lipophilicity. The lipophilicity is a compound's ability to solve into lipids. And in the body, that's extremely important because the cell membrane is made up of a phospholipid bilayer. So for these drug compounds and these chemicals that are supposed to heal you to get into your cells, they need to have the correct amount of lipophilicity so that they can actually get from the bloodstream into the cells and diffuse into there so that they can be effective. And so that makes the bioavailability of this drug more effective. So you might have heard of some of these drugs. I'll get into them in a little bit further. But the main thing is that this group actually is found on a lot of prescription drugs. So the reason that we focus on trifluoroesters, or esters made out of this trifluoromethyl group, is because it's an extremely simple synthesis to make this group. I came in there and about 2 or 3 days into it, I was making these esters 2 or 3 times a day. So that kind of really speaks to the simplicity, the practicality of this particular compound. I can make it, it'll be very useful for the pharmaceutical industry. Trust me on that. As you can see from this graphic right here, all you have to do is you add a carboxylic acid to an alcohol, possibly with a solvent, a catalyst, and you end up with your ester and your water as the byproduct. So what you're going to notice throughout this presentation, what you might have noticed throughout all the presentations, is that it's all about getting more effective, more simple, more practical, and that's what we're trying to do here. So do we have any pharmacists here? Thank you. You can always count on your mom to bail you out on that. She really is a pharmacist. So you might notice, or you might recognize some of these structures right here. Celebrex or celecoxib, that's a non-steroidal anti-inflammatory drug used for arthritis treatment. It's also the 26th highest selling drug in the US in 2012. Januvia, that's used for type 2 diabetes. That's the 22nd highest selling drug in the US. So what you can tell from here is that the health effects are widespread, as well as the implications for the industry. The rest of these, this is a Sustava, that's an anti-HIV drug, Prozac, that's an antidepressant, and Prevacid, an antacid. So the health effects of this trifluoromethyl group, which you can actually see on all of these compounds, right, the CF3 group, the health effects are very widespread. A lot of different ailments, a lot of different situations can be helped by drugs that use this compound. So the implications of our research are pretty widespread if you think about it in terms of the industry. Another thing you might have heard in one of the earlier presentations is green chemistry. That's a new subset of chemistry where you're trying to make chemistry more helpful for the environment, more environmentally friendly. And ways that you can do that is stop using toxic catalysts, toxic reagents, or something that's going to, when you dump it out, it's going to cause some sort of harm to the environment. Not only is this useful for the environment, but also to the PI, or the investigators that are doing this. For example, when I use something like benzene, I get a little afraid because I know for a fact that's a carcinogen. So if we can try to avoid using volatile or toxic substances in the lab, I'm sure people would be a little more comfortable when they're doing these experiments. And so not only is green chemistry important in general, but the pharmaceutical industry really caught on to this. So in 2005, they had a roundtable discussion, including companies such as AstraZeneca, Merck, Pfizer, GlaxoSmithKline, and they wanted to come out with 12 key areas that they wanted to improve in pharmaceutical development so that they could stay within this green chemistry boundaries. One of the things they came up with was greener fluorination, and that's basically what this research is about, is fluorinating a compound so that this fluorine compound or this trifluoromethyl group can be effective. And so a lot of research has already been done into this. People have tried solvent-free reactions where you don't even have to use a solvent, so that's less waste. Some people have tried better catalysts, and that's where we focus, on better catalysts, because in the past, the catalysts for esterification or trifluoroesterification have been heavy metals, super acidic, So these are extremely expensive, rare, possibly toxic, and possibly harmful to the health. So you don't want to use those, especially in a pharmaceutical compound, which is why we came upon using iodine. Iodine is a very versatile catalyst, especially in esterification. There have been a lot of research done into it. In fact, one of the papers that was cited in my main paper looked into iodine for about 30 to 40 pages and all different types of oxygen-containing compounds and how you can use iodine to catalyze those reactions. So it's an extremely versatile catalyst. And based on what we had in the lab and what was convenient, we tried to focus on using sodium iodide and I2 as our two main forms of iodide that we use for this research. So to sum up the applications, this research will help us figure out things that are good for health, good for the industry, good for the environment, and good for science. Because if you think about it, if we can figure out the mechanism behind some of these reactions, you can apply that knowledge to even similar reactions to other different science. So basically, my research is really important. That's what I want to tell you. So let me get into the methodology a little bit, what we did on a daily basis. First thing we had to do was to actually synthesize the trifluoroesters. So what you do here is you add an alcohol, and we use various different alcohols, as you can tell, to either an acid or an anhydride. We use trifluoroacetic acid, TFA, or trifluoroacetic anhydride, TFAA, and that's where you got the fluorine on the finishing ester from. And so you added those in vials, stirred them for a while. You could range, the reaction ranged from 30 minutes to 24 hours, from room temperature to 85 degrees. So there's a lot of changing around going on in those reactions. And one of the things that we did with trials was we used different solvents because we wanted to figure out what would be the most effective solvent. So we tried a lot of different things because we want to really optimize this reaction, figure out the best, most efficient way to get this ester in the end. How we monitor these reactions, we use thin layer chromatography and nuclear magnetic resonance, NMRs. Basically, Perry did a really good job of explaining what an NMR is, but it's just a graph of peaks that tell you where the carbons with protons are on something. And we could also use a fluorine NMR in some of these cases because the finishing product had to have fluorine on it, and it would give us this one straight peak that told us, yes, indeed, you have formed the product that you were looking for. So that was very important in monitoring the reaction. So we had two things to do after the reaction was complete. We could collect the yield in two different ways. First, we could purify it, and this would include extracting it with DCM, adding an anhydrous to take out the water, adding magnesium thiosulfate to get the iodine out of the reaction, and then you would rotovap it down and put it on a column, which allowed you to separate the starting material from the finishing product. At the end, you would weigh this and find out what your yield was compared to the theoretical yield, and you get yourself a good percentage. A easier method was NMR yields. Basically, you would take an NMR of this product, and you would get your peaks of your starting material and your product. And these were literature notes, so it was very easy for us just to compare the ratios of those peaks to the finishing product peaks. And this allowed us to figure out what the yield was, what the conversion was. So this is just a quick graphic of what's going on. This is an example reaction that we ran many times. This is benzyl alcohol right here, and you end up with a benzyl ester using that alcohol, and with the OCOCF3 group, that's your finished product, that's your ester. You could go one or two routes getting the yields. So let me get into the results now. The first thing we did was run a solvent screen. We wanted to figure out, going forward, which solvent would be the most effective. And what we found is that nonpolar solvents are the most effective. This includes the hexane, benzene, and your diethyl ether. On the other hand, polar solvents were not effective, DCM, and particularly water. The first thing we noticed when we finished the trial is A, we can use hexanes going forward, which is what we did, and B, water didn't seem to completely stop the reaction, but it definitely had a strong hindering effect on it. And one of the things that we were trying to figure out is there a way we can run this reaction in water? So we kept that in mind, and we moved on forward. The next thing we wanted to do is figure out which form of iodide would be more effective, I2 or sodium iodide. And what we found here is that there was really not much of a difference between the two forms of iodide. So we got just about the same yield for both of them when we ran them with two different alcohols. From that, it was basically our choice. And so we ended up using sodium iodide going forward because of ease of use. If you've ever worked at I2, you know that it melts onto the weighing paper, and so you can't actually transfer it to the vial. That was a very frustrating first few days for me. Moving forward, the first thing we did was, after we figured out that we're going to use sodium iodide and hexanes, is that we just ran some of the reactions with sodium iodide, but no water. So with the hexane solvent, we're solvent-free. And as expected, we got higher yield when we used the catalyst. So let me this first thing right here, where we ran no water in there, just wanted to see if the catalyst is effective. With 3 different alcohols with various different structures and properties, we got higher yields for the ones with the catalysts. So that's something you would obviously expect. But one thing that we noticed while we were doing these reactions is that at the beginning, when we would take TLCs, if we took quick NMRs at the beginning of the reactions, we would seem to find that the reaction without the catalyst almost had the same yield as the one with the catalyst. And so this didn't seem to make any sense. But what would happen is, as we went on with the reaction, we took later NMRs, we would find that the one without the catalyst kind of stopped, whereas the one with the catalyst kept going. So we looked into this a little more when we started using water as a solvent. Now, as mentioned earlier, water could not be used as a sole solvent because that would get us very low yields. We ran that once and we got about 1 to 2% yield. So that wasn't very good for us. But what we did was we ran these reactions in a 3-to-1 solution of hexanes to water. So we had a little bit of water in there, almost to simulate as if you had a trace contamination. And just to see if this could be made more effective if we looked into a little more. And you'll see it a lot better on this graph right here. You kind of start off at the same level yields. That's not good. But then you get this plateau right here on the ones without the sodium iodide. You climb back up and then you get this plateau again. Whereas when you're using the one with sodium iodide, you have an upward rate of reaction going the whole way through. So what this seems to imply to us is that when there's the water in there and no catalyst, it seems to get stuck in an equilibrium state where water is trying to hydrolyze and the esterification is trying to continue. So these two reactions are competing and the esterification is not favored. But when you use the catalyst, the esterification is favored and you actually end up with yields that are near full yield. So we had about 96, 97% right here. This showed us that the catalyst is not only effective in the absence of water, but also in the presence of water, which led to the possibility of the green solvent. Going back to the green chemistry approach, if we could use water as the only solvent, it's obviously very non-toxic, very easy to use, easily accessible, pretty cheap. So this going forward could make this process a whole lot simpler if we could make this even more effective to use water solely. But at least we're able to use water in a little bit, so that's a good step forward. While running these reactions, all of you people who work in science here will completely get this one, where you're trying to answer one question, at least one more is going to pop up at the end. And this was our main question. When we ran these reactions, at the beginning of the reaction, if we put sodium iodide into the solution, we would get a light reddish color. Except when we took it out at the end, we got a purple color, which indicated that the sodium iodide had been converted into I2. We had no idea why that happened. So going forward, that's going to be something that we really want to figure out, because we're pretty sure that this will help elucidate the mechanism. This is actually not the only instance of this occurring. It also occurred in a reaction a long time ago, documented in a paper, where they were also using fluorine-containing compound. So it might have something to do with the fluorine and the TFA. And so going forward, my group over there is going to figure out why that happens. This is just another way of looking at it. As you can see, numerically speaking, the ones without sodium iodide, 57, 57, 75, 75. So they get stuck there. Whereas the ones with iodide, they start off kind of low, and then they end up here at the 96%. So that is a good effect of the catalyst. One of the last things we tried to do was put our own guesses towards exactly the mechanism of the reaction. How is iodide catalyzing this reaction? And so what we did was we ran the esterification reaction with a secondary chiral alcohol called S-phenylethanol. And in this situation, you could get two possible outcomes. You could get a racemic product, which would mean you would have a mixture of different enantiomers. So these are the same compound really, but different orientations. Or you could get the same enantiomer, you could get an enantiomer-rich product, which is what we got. We got 99% of the same enantiomer. And what this implied to us is that there are two possible mechanisms for how this reaction works, we think. First off, you could have iodine attacking the TFA, which activates it, and possibly turns it into TFAA, trifluoroacetic anhydride. And reactions seem to work a whole lot better in the TFAA. So this might be what's happening, making the reaction faster or having a higher yield because of that. In that case, I2 would act as a Lewis acid. The other possibility is that this intermediate right here, acyl iodide, is being formed. So that means the iodide is coming onto this area right here. And this iodide is very easily replaced by the alcohol right here. So if you look at the finished product, you have the alcohol, and then you have your OCOCF3 group. So once you have this right here, you can just replace that with the alcohol, and you have your finished product. So that's one of the possible mechanisms. So just when we had finished all this, we wanted to make sure that it wasn't that, iodide is like a one-trick pony or something. It just worked with that alcohol. We ran it with a bunch of different alcohols, pretty quick reactions right here, and got moderate to high yields with different structures, different properties. And so this shows the versatility of the catalyst. This shows that, iodide can be used in various different situations when trying to make trifluoroesters. So to conclude, what we do know for sure is that a lot of conditions, temperature-wise, time-wise, work well with this reaction, but you want to be sure to use nonpolar solvents. That's going to get you higher yields. We do know that iodide is an effective catalyst for this reaction, both in the absence and the presence of water. And it's particularly important that it does so in the presence of water. Further research will be to get that catalytic activity even better so that you can use water as the only solvent. The sodium iodide to I2 conversion raises a lot of questions, but we're pretty sure that once we can figure out why that's happening and how it's happening, we can figure out a mechanism. So the main thing is now the mechanism of this reaction needs to be clarified. Thank you all for listening. I just want to acknowledge a few people. Professor Wangmin Dong, he's actually not here. I think he's in China, but I'd like to thank him for letting me use his lab and his resources. My two mentors, John Thompson and Brandon Reynes. Brandon's not here, but they've been a great help. They actually let me, I know how to do chemistry now, and that's really because of them. So thank you so much. I'd also like to thank Nick Savage, who filled in for a little bit, and he was a great friend as well. So the entire group, Rachel as well, very helpful, very nice, and let me be comfortable in the lab. I'd like to thank the Welch Summer Scholar Program and the Welch Foundation as a whole for organizing this great program. Dr. Stevenson, thank you for being the state director. Taylor's not here, but she did a great job as well. And Jen, thank you so much for the meeting. Thank you so much for putting up for Kevin and I being late to the meetings once in a while. Thank you for bringing out the food so we could feed the turtles. I enjoyed that. And thank you to the University of Texas at Austin for their hospitality, and especially, last but not least, my family for their constant motivation. Thank you so much, guys.
Question?
Well, more of a comment. I think it's really exciting that you're able to get a catalyst that favors one enantiomer, especially given there are several examples in the pharmaceutical industry where one enantiomer is a medicine and the other is toxic.
Yes.
So that's really important. That's pretty cool.
And a lot of things is you have to be extremely careful with these type of reactions because they're going to be pharmaceuticals, so you don't want to mess up with them. Give someone what you told them, and medicine turns out to be the exact opposite.
How did you determine the catalyst concentration? Was it
We started off with using some literature that we're running just general esterification, and normally they were using about 10% of the catalyst, so we tried that. Some of them we tried actually, adjusting the concentration, but it seemed to us that the 10% was actually convenient, because if you're trying to measure out like 5 grams or 5 milligrams of sodium iodide, that does not go very well. So when you up that a little bit just for convenience purposes or scientific purposes, the reaction is